We got so many likes for this experiment, this demonstration actually. So I thought that I should leave it up after 10 years, this experiment. Let me just take it and see in what shape this experiment is. These are all the experiments, that demonstration that I did in 2010. And let's see how it is. So this is the same. Wow, look at this. This has gone little loose. I think it is because of the temperature change, you know, it has expanded a little bit, thermal expansion, I guess. And otherwise it looks like, it doesn't look like it's broken. I have this magnet intact. I think, yeah, it's still working perfect. The magnet is there. Oh, I have some nails. So I'm going to try and test this experiment one more time again and see if it is still working. And I have all of those experiments from that time. Wow. I saved it. Good, I saved it. So this is the same board, same nail, same coil. 10 years before we made it. Wow. And do I have the wires on there? No, I have the wires. Okay. So what I'm going to do first repeat the same experiment, and then I'm going to make the changes into it. What were some comments into the comment section that I must use a stronger magnet. And for the stronger magnet, I bought this ring magnet. They are very extremely powerful. And I have this small little guy over here also. This is also very small powerful magnet. And I'm going to try this one also. Let's see which one. And instead of putting some iron core, I have these nails, I have these staples, or maybe these pins. I mean, I'm going to try it, whichever works, I don't know. What I also did, I pulled out a milliampere meter also today from my closet and see if this one can work. Okay, so I have two set of wires here. One is this one, the one that I think I originally used with the experiment. It was into other closets, so I pull it out. And I'm going to probably use these ones because I think this one has a thicker cross-sectional area, so probably less resistance. Let's see which one works. This is just a magnet, which we will see. Okay, so the first thing that I'm going to connect it to the microampere meter, and let's see if this experiment still works. I wonder. So you see that the microampere meter is absolutely calibrated. Still, it's the same intact. It has not changed. This is the same microampere meter which I used 10 years before. So I'm living that experiment again. Okay. So the idea is that this is a coil and this is a magnet. Magnet has a magnetic flux, means the magnetic lines of force. When I move this magnet on this, the flux which is passing through this coil, or the flux which is associated with this coil, is going to change. And according to the Faraday, whenever there is a change in the magnetic flux, it induces an EMF, and if the circuit is closed, it induces a current, and that is called an induced current. So let's see. I used the microampere meter at that time because the deflection was very weak and ampere meter was not able to detect it. But we'll see, we'll try with the milliampere meter if there is any kind of reductions into it. Let's see. So this, I'm going to give it a little try, and I'm going to see this deflection here is going to be very kind of weak here. Let's see if there is at all any deflection. This is not showing any deflection. So either there is a break in the circuit, or these wires are not good anymore. So I'm going to change this wire again, and assuming that there is no break in this coil. So let me change this wire and see if this one works. The bigger, thicker wire. Maybe this microampere meter is also not working. I don't know. I haven't used it from a very, very long time. So let's see if this one works with it. No, this one is not working either. Okay, if this one is not working, so let me change the other wire. Probably this is very long, so maybe it has, because of the length, a very large value of the resistance. So let me try this. Okay. I would also, I think another thing that I should do is move these magnets very far away, because these magnets are very, very powerful. So maybe they're kind of nullifying the effect or something. That might be quite possible also. So let's see. Keeping the fingers crossed. Let's see if it works this time. Yes, so I think it was those magnets that was in the close. You see the moment I move it, you can see the deflection. Now somebody suggested me that it is the opposite polarity that is like kind of canceling. So let me just move it in one direction and see. It's still kind of deflecting in both the directions. It's like kind of just telling me the presence of current into the circuit. Very weak current though. So now I'm going to change it with this wire that I'm assuming has a lower resistance. These two wires has comparatively lower resistance because they are thicker. And let's see if this one gets better, any better. And then I'm going to use stronger magnets and see if it gets any better with the stronger magnets. So this is the first change I'm doing. Like instead of using the thin wires, I'm using a thicker wire. Although this is a little longer, but I think because cross-sectional area is proportional to the square, so and it's in the denominator, so it might have a bigger effect on the resistance probably. I see a little bigger deflection in this case. I think the resistance has decreased, so I see a little bigger deflection. I definitely see a little bigger deflection in the microampere meter with when I was using the other wires. So definitely by using a thicker cross-sectional area, the current that is produced, induced, that is inducing into this one is growing up a little bit more because the resistance is less in the circuit. Now I'm going to use a stronger magnet. So stronger magnet means I got these powerful ring magnets, and then maybe I can use those ring magnets. They're so powerful, I have to be careful. They can crush my hand if I'm not careful with that, if just my fingers are in between. So let me just use these 3 of those. I didn't even open up this one. Let me open up this one. These are universal pacer test magnet. Oh, these are like medical magnets or something. Let me just open it and see if this one is better for me. This is 2. Oh, this is so strong. I can't. This is like, no. All right, let's see. This is a stronger magnet. I'm going to move this magnet away so that it does not cancel its effect. And let's see. No, this one is not working much. This one is really not working. I'm surprised why. Because it's a smaller size magnet? I don't know. And let me try that one back again. Did I put the molybdenum magnet closer? This was, just now it was working, but now it kind of stopped working. What happened? I do not know. Okay, maybe the connection got loose. That's interesting. So what happened? So I moved the magnet out. This magnet is moved away. No, this is not showing any deflection. That's I'm surprised. That's surprising. No, this is not showing any deflection either. Okay, why it happened? Let me try back again. It was giving such a good deflection. Did I change anything? I did not. Okay, it's coming back like, but something is bothering it. I do not know what is that. It's still giving a little deflection, but not as powerful as it was giving it before. And if I combine all the magnets together, what happens? Let me see. If I put these ring magnets on the top of this ring magnet, does it works better? Yeah, the reflection gets a little better, but I think it is kind of the same. So stronger magnet is definitely producing a bigger amount of, okay, let me just push it in one direction for, yeah, you see? And it comes back. Yes, so that is, so the flux which is associated with this coil is changing, and this changing flux is inducing an EMF, and because this circuit is closed, it is inducing a current, and the current is still weak. Can I change this to a milliampere meter and then see if it can detect something? I doubt, because there's a huge difference between micro and milli. Let me see this. This is for 500 milliampere, 50 milliampere I'm going to use for 50. Let us see if this one works. It is slightly moving. If you carefully look into it, it's very slightly moving, and it looks like that this medium, it's very slightly moving, but in this one, in the micro, it is moving a little stronger. The other suggestion that was given to me was that put some iron core. I couldn't find anything, but I thought maybe these iron pins, which are like which are kind of I think ferromagnetic material. If I push it in, is that going to be helpful at all? I don't know. There should be soft iron core. This is not a soft iron core, so I don't know. I doubt if this is going to help at all. It has to be soft iron core. Let me see if that one works better. No. Oh, this one is making this one vibrate even because of that magnet over there. There is definitely deflection in this one, but it is not helping at all. It has to be stable, and it has to be soft iron core. I don't know how to do that. You guys can suggest me what I can do in that. But definitely by changing this wire, I saw that, and by making using powerful magnet, the flux has increased, and then the EMF that is generated is bigger in this case, and as a result, the induced current is stronger. So what is flux actually? The flux is, this is a magnet, like, and this is a north pole and this is a south pole. So if you have a magnet, north pole, and this is a south pole, this is the north pole, this is the south pole. So the magnetic lines of force actually are closed curves. So they go from north and they go to south, from north to south. And inside the magnet, it travels from south to north. So if this is a powerful magnet, then you have more lines. The one big thing about these magnetic lines is that they never cross each other, because if they cross each other, then at this point, the direction of the magnetic field is 2. I have 2 directions of magnetic field, which is not possible at the same time. So these magnetic lines, they never cross each other like electrical lines. Electrical lines are not closed curve, but the magnetic lines are closed curve. So if I put a plane, so let's say this is a magnet, and if I put a plane in front of it, this is the north pole and this is the south pole, And if I put a plane in front of it, like a wire or like a coil, then these are the lines, magnetic line that passing through this. And the angle between the perpendicular of this plane and these lines is 0 degree. So the flux which is associated now, the total flux which is associated with this coil, which is represented by the symbol phi, is nothing but the product of the magnetic field B and the cross-sectional area A of this coil. If this plane is not making, so the case is this, like if I have this plane, if I have this magnet, and this is, let's say this is the coil, and this is the North Pole. And this is the condition now. So you see that the most of the lines of force will pass through this. So the angle between the normal to the plane, this one, and this magnet is 0 degree. So basically it is nothing but the dot product. So the general formula for the phi is B cosine theta times A. If the angle theta is 0 degree, then cosine of 0 degree is 1. So the phi will be maximum, and the maximum value of the phi will be B times A. But if this is in the direction of the plane, let's say this is the direction now. Let's say this is the direction. So the normal to the plane, like this one, then the normal to the plane is making an angle of 90 degree with the magnetic flux direction. So in this case, the value of phi will be, value of theta will be 90 degree, and phi will be B times A cosine of 90 degree, which is 0. So phi will be minimum. So that is what is happening now. I don't know what type of magnetic field it is creating and how it is changing, but definitely the magnetic field or magnetic flux that is associated with this coil is changing when I move it, because right now the magnetic field is constant. You see there is nothing. The moment I move it, it moves. So it produces it. So whenever there is a change in the flux, magnetic flux associated with the coil, an EMF is induced according to Faraday, and in turn induces a current into the circuit. This is a very simple experiment done by the Faraday, which is also called by the name of electromagnetic induction, and has helped many other discoveries to happen. So I thought that revisiting this experiment would be worth, because I have so much of comments on this particular experiment. And definitely some comments that you guys gave me that changing the wire or putting a flux into it or making a stronger magnet has kind of made more deflection. But I will definitely continue working and seeing how I can make even the deflection more. Maybe I will try to change the type of the coil or the material of the coil or something like that. Or maybe I will take more turns into the coil or something. And let's see. That's it for now. Thank you.